It's as if there's something going on behind the scenes that is hidden from us. And to me, it felt like a conspiracy. If you take this kind of theory seriously, it's telling you that the fact that we can't send instantaneous signals is not a law of physics. It's an accident of the special state that we live in. So I want to control my robotic lander on Mars in real time. We can't do that now. It takes 20 minutes for a command to reach the lander. You know, in principle, a kind of instantaneous communication would be possible. Which means, of course, you have to revise relativity theory.
Hello, welcome back to the Quantum Foundations podcast. I'm Maria Villaris, and today I'm joined by Antony Valentini, who is going to be speaking about the work that he's done on a theory of quantum mechanics. Thanks for joining us, Antony.
My pleasure.
And Antony has written a book recently called Beyond the Quantum, which is on the topic that we'll be covering today. But do you want to tell the audience a bit about the book before we get started?
Well, it's a book written for the general public, with an eye on fellow scientists as well. It's based on research I've done the last 35 years into the de Broglie formulation of quantum physics and how it points to a physics beyond the quantum mechanics that we know, and how one might discover this new and deeper physics beyond the quantum. That's what it's about in a nutshell.
Mm-hmm. Yeah, great. Yeah, very exciting. So, yes, the topic of this podcast will be, if you've kind of heard of different interpretations of quantum mechanics, you may have heard of one referred to as the pilot wave theory or de Broglie theory, and Antony has done a lot of work in this direction, and that'll be the topic that we'll be talking about today. So before we kind of get onto that, first, could you tell us a bit about how you became interested in looking at quantum mechanics in the first place, and
in general,
in this area as well?
Well, in general, I became interested in physics because I wanted to understand general relativity, Einstein's theory of gravity, and which I still think is the most beautiful theory in physics. But after that, then, well, there was this other great mysterious theory, quantum mechanics, which I'm still trying to understand. But these ideas in particular, my trajectory was perhaps a bit unusual in that I was intrigued by the evidence. I mean, here I'm going back to the 1980s. I was thinking about these things where a consensus was beginning to emerge that quantum mechanics is in some sense non-local. There are what appear to be instantaneous connections between distant objects. So if I have two particles that are what's called entangled, which just means that there is one wave that describes both particles together. You can't define a quantum wave for each particle on its own. These entangled particles, doesn't matter how far apart they are, they seem to be communicating in some way that is, depending on who you talk to, and is not really clearly defined, but in some sense they're communicating. And of course there's controversy about this. Here's what I found bizarre, is that, well, they seem to be communicating, but you can never use these effects to send an actual signal. If I've got one particle, you've got the other particle, and I want to send you a message, it doesn't matter what I do over here. The actual statistics that you gather here, if we do experiments with many particles, many copies of these entangled particles, and you make measurements on your particles and you gather statistics of the kinds of measurements, outcomes that you've seen, the results that you get are completely unaffected by the fact that I'm over here, I have a particle that's entangled with yours, and maybe I'm doing things to mine. I can't send you an actual message. Mm-hmm. And yet, some general reasoning given by John Bell in the 1960s, where he was looking at the peculiar statistical correlations between these particles, he was able to show that essentially, if there is some underlying reality to these particles, then in order to explain the strong correlations that we see between the two particles, they have to be communicating instantaneously. That is essentially what Bell's theorem tells us. So I found this really puzzling, because it's saying that, or it seems to be saying, there's something instantaneous going on behind the scenes, but you can't actually see it or control it. Okay? Mm-hmm. I mean, that's what it's saying. That these particles, they're somehow communicating, but you can't really put your finger on it and use it in practice.
So you're interested in the fact that it kind of only goes so far.
To me, it's tantalizing. As I said, it's as if there's something going on behind the scenes that is hidden from us. And to me, it felt like a conspiracy. You know, why would it be that it's as if relativity, I mean, of course, according to relativity, you're not allowed to have signals going faster than light. So, you know, if you have things communicating faster than light, that's supposed to be a big problem. But in practice, relativity is all right because there's no actual signal. So, to me, this felt like a conspiracy at the foundation of physics, that something is going on that's not supposed to be going on, and we can never actually see it and control it. And to me, it seemed that the uncertainty principle is supposed to be a fundamental principle of physics that sets limits on what we can measure and how accurately we can measure things. It seemed to me that the picture that formed in my mind is that there are instantaneous interactions going on. But this uncertainty principle, there's a sort of statistical uncertainty noise that is getting in the way of you actually seeing it directly and using it. You can deduce it's there from Bell's theorem by being clever. You can mathematically you can deduce it's there, but you can't actually see it directly. And so I started thinking that maybe a way to understand this would be that the world that we live in is really a special state. The world that we live in is in a special state, a little bit like thermal equilibrium. So in the 19th century, physicists were worried about what would happen in the far future, because now we have different systems at different temperatures. The sun is very hot, the earth is cooler, the bottom of the ocean is even cooler, there's a hot cup of coffee, there's the room temperature here. These differences of temperature will eventually settle down to one uniform temperature. So the cup of hot coffee cools down to room temperature. The stars will eventually burn out. It will take billions of years, but they will eventually burn out. And this was called the heat death of the universe. One day in the far future, when everything reaches the same temperature, because there are no differences of temperature, you can't convert heat into work. You need differences of temperature to convert heat into work. And that is why it's called the heat death of the universe. Now, in such a universe, if everything's at the same temperature, everything would have the same thermal noise. Okay, there's a microscopic jittering motion. So molecules at a certain temperature, they're jittering. This is the sort of thing you associate with Brownian motion. And the level of jittering is set by the temperature. So if everything was at the same temperature, there would be a sort of irreducible thermal noise in everything. Now, you imagine if there were beings living in such a world, and of course beings couldn't live in such a world because that's why it's called the heat death, but just imagine if there were beings in such a world, they would think it's a law of physics that all systems have this irreducible thermal noise or jittering. And if you try to probe the fine details of molecular motions, well, if your equipment is at the same temperature as the molecules, you'll find that, well, you can't really, you're trying to probe something accurately, below a certain noise level, but your system has the same level of noise. And so you can't really see clearly what's happening. So this would be seen to be a law of physics, some fundamental limitation on what we can measure. It would also, beings in such a world would think it's a law of physics that you cannot convert heat into work. This is a huge reservoir of heat energy, but you can't do anything with it. And that would be seen as a law of physics. Now, if we were looking at beings in such a world, we would say, look, you're mistaken. These are not laws of physics. What you're seeing is just a special state of global thermal equilibrium where everything happens to be at the same temperature. Everything has this irreducible thermal noise. You can't convert heat into work. These are not laws of physics. They're just accidents of the state you happen to live in. Now, I started to think, this was before I studied pilot wave theory, I started to think that something like this must be going on in quantum mechanics, that there are instantaneous superluminal connections between objects. The reason we can't see them is because everything has reached some kind of state of statistical equilibrium where all systems have the same quantum noise, uncertainty noise, and it's that noise that is stopping you from seeing the details and from being able to actually use entanglement to send a signal. So on this view, the fact that you can't use entanglement to send a practical signal is not a law of physics, it's an accident of the state you're in. Now, you know, this was, I mean, back in the late 80s, and I didn't really have a theory. I was playing around with these ideas and I was imagining what I called a subquantum demon. You imagine a demon who somehow was able to see more precisely than the uncertainty principle allows.
Yeah.
And how we would then be able to use entanglement for superluminal signal. I was playing around with this stuff.
So kind of like a Laplace's demon in thermodynamics, but for...
Exactly, or Maxwell's
quantum.
demon in thermodynamics. Yes, instead of Maxwell's demon, it's the subquantum demon. You can call it Valentini's demon if you like. Anyway, but there we go.
For context, these demons being like hypothetical beings that have an immense amount of knowledge about the scale that we're discussing.
In fact, what I was saying earlier about, you know, in a heat-death universe, if you had, you know, your equipment is at the same temperature as the gas molecules that you're trying to probe, I mean, it's exactly the kind of thing that Maxwell discussed in the 19th century. Maxwell's demon, imagine a being, he's trying to sort fast and slow molecules. And the problem is that, well, if the equipment you have and the trap door, and there's a long discussion about this, but if they're all at the same temperature T, you find that the thermal fluctuations in the equipment stop you from doing anything useful. So anyway, the subquantum demon. But now, but, you know, I didn't have a theory, I was playing around with this. And then I came across John Bell's wonderful book, Speakable and Unspeakable in Quantum Mechanics, which had just been published a couple of years earlier, in 1987, where he has a few chapters devoted to pilot wave theory. It's a sort of pedagogical account of the Breuer version of quantum mechanics and how it works, which I had read a bit about, but I'd had the impression that it wasn't really a fully fledged formulation of quantum mechanics. It could only explain some simple phenomena. Reading Bell's book, I realized, hang on, there is actually a formulation of quantum mechanics with trajectories in which, as we see here, particles are guided by waves. In pilot wave theory, there is a wave, which is the usual quantum wave that we talk about in the textbooks. In addition to the wave, there is a particle that is guided by a law that says the particle moves perpendicular to the wave crests. So here in the classic two-slit experiment, the quantum wave comes in, it hits the two holes, you get a wave here and a wave here. These two waves here overlap, and you get a complicated pattern of wave crests. The particle is moving perpendicular to the wave crest, and it wiggles around the funny way and ends up somewhere. Anyway, that in a nutshell is pilot wave theory, which, you know, as became clear reading Bell's book, actually, it is a little used, little known formulation of quantum mechanics, but it is equivalent to quantum mechanics. Now, most people leave it there. What struck me, and I think because I had been wondering and thinking about this already for 2 or 3 years, this idea of this sort of quantum death.
Mm-hmm.
When I saw the Broglie theory, I immediately realized this theory is saying exactly what I've been talking about. In this theory, if you assume that the particles begin, so here, if I repeat this experiment many times, in general, maybe in one run of the experiment, the particle starts here, in another run it will start somewhere else, in another run, and it will land somewhere else. So in this theory, you usually make an assumption about the distribution of particles as they come in. You assume that over many repetitions of the experiment, the particles are distributed according to the shape of the wave, specifically the square of the height of the wave. So here the wave is uniform, so you assume that over many repetitions you would have a uniform distribution of particles coming in.
Mm-hmm. So if you were putting the screen at the beginning, you would get a uniform
You
distribution.
would get a uniform distribution, exactly.
Mm-hmm.
Now, what happens, you can show in the theory that if the particles are initially distributed according to the square of the height of the wave, as they move, the distribution stays that way. It stays proportional to the square of the height of the wave. Now, at the backstop, the square of the height of the wave looks like this. So if you fire in many particles, and you see, one lands here, one lands here, one lands there, you'll find more land where the wave is large, fewer land where the wave is small, and the total distribution matches this pattern. Now, sorry, I've gone on a bit of a long detour here, but the point is that in this theory, if you assume that the particles have this initial distribution that is given by the Born rule, maybe I should write that down. I should say that the Born. So the Born rule, so that the particles are distributed, in this case, uniformly, okay, over many repetitions, have a uniform distribution. Now, if you assume that distribution, you get the same predictions as quantum mechanics. If I assume a different distribution, I get something else. So, for example, if all the particles started at this point, they would all land there. There wouldn't be any interference pattern. If they all started in a small region here, they would all land in a small region around here.
Yeah.
In fact, if you look at this, if all the particles started in the top half, because of symmetry here, they would all land in the top half. There would be nothing down here. So what you get depends on what you put in.
Right.
So now, if you take this theory seriously, it's telling you that quantum theory is a special case of something broader. If I assume an initial uniform distribution of particles, I get the agreement with quantum mechanics. If you have something else, you get something else. So now, what has this got to do with the heat death?
Sorry, just on that point,
yes.
Isn't there something else kind of also described by quantum mechanics? Like, but instead of saying that it's a wave coming through, it's like saying, so if you've got the particles only here, is that corresponding to like a situation where this, no, I guess you're saying that it's not something that corresponds to a situation where this
is
something different.
It's different.
Yeah.
So if you close this slit, then you only get that wave. There's no other wave here, and you'll just get a hump here.
Yeah.
Okay? No. If you have what I'm talking about, this is not possible in quantum mechanics. If all the particles were starting just in the top half here, you would have both holes open. You would get half of the wavy pattern. You would get this wavy pattern, and here there would just be nothing.
Yeah.
which is completely impossible in quantum mechanics. In quantum mechanics, I mean, the situation, what I'm saying is, if the particles start with an anomalous distribution, the wave is not changed. The quantum wave is the same. The square of the height of the wave is still this. So according to quantum mechanics, if you repeat this experiment many times, you must see this pattern.
Yeah.
In pilot wave theory, it could be that you see only half of it. It could be that all the particles land here.
Yeah.
It just depends on what the initial distribution is.
Yeah, so you're saying there's a degree of freedom, a kind of new degree of freedom, which is what's the distribution of these input particles.
Exactly.
And quantum theory is a special case where that distribution is kind of uniform.
Exactly.
And that's when you see this kind of wave-like pattern.
Exactly. Exactly.
There's a whole space of other cases where you can imagine different distributions which would give different outcomes.
That is exactly right. So now the question is, if you take this theory seriously, why do we always see this distribution? If I go in the lab and I fire particles at a screen, and and then I fire another one, and I've prepared this certain quantum wave, I always find this uniform distribution. That's what we find if you go in the lab here at the Clarendon and you do this experiment. You will always find the usual wavy pattern.
Yeah.
Which in pilot wave theory means the particles started with a uniform distribution here. So now, this is where I started working on this theory, is to try to understand where do these initial conditions come from? Okay, why do you always have the same initial distribution? And the answer I came up with, that is a state of statistical equilibrium. If you in pilot wave theory, if you begin with a system of particles where the distribution is different from the quantum wave, but where the quantum wave has a certain degree of complexity. I mean, this is too simple here. If I started with particles that are all up here, they're all going to stay up there. But if I have, say, particles in a box, and I have a quantum wave that is a sum of several energy states, okay? So the wave, it sort of looks like this, and it sloshes around as it evolves in time, okay? And according to quantum mechanics, that is the probability distribution, and it must always be that way.
Yeah.
In pilot wave theory, if I begin with particles that are, say, for instance, bunched in one corner of the box, and you let them go, you find, because of the complexity of you've got this sum of different energy waves, the trajectory is very complicated. I mean, here you see it wiggles a bit, but in a box, if I have a sum of several energy states, the trajectories are extremely complicated. They're very erratic. And if you begin with a distribution of particles that is different from the shape of the wave, if you let it run, you find that very quickly they spread out in a way that matches the square of the height of the wave. They very quickly evolve towards the Born rule. And this has been, I mean, I could show you figures from the book, I suppose, but there are some figures shown in the book of some computer simulations we did 20 years ago with Hans Westman, who was a PhD student in Sweden. We were amazed, actually, at how rapid and efficient this process is. It was particles in a two-dimensional box, a sum of just 16 energy states. And it's a periodic system, which means the quantum wave, it evolves, and after a short while it comes back to the same form that it had. Okay, it's a periodic system. Over just one cycle, so the wave function it sort of looks like this. It has several humps and troughs, peaks and troughs. We started out with a distribution that was just a simple hump in the middle of the box. Over one cycle, the thing was almost indistinguishable from the square of the wave function. So now what does that mean? So now let's go back to this question. In the lab, why do I always find that in this experiment, why do the particles always come in uniformly distributed? Well, let's think about those particles. When you go in the lab, maybe you're doing this experiment with electrons, and you're firing electrons one at a time at the screen.
Yeah.
Where did these electrons come from? They weren't sitting in the lab in a vacuum for billions of years waiting for you. They have a history. They've been knocking around with other things. If you trace back the history of those particles, it goes back to the formation of the Earth, the formation of the solar system, all the way back to the Big Bang. Mm-hmm. Okay? So the point is that any particle that you experiment with in the lab, it has a long and complicated and violent astrophysical history. Mm-hmm. So the kind of process that I described where the distribution rapidly evolves or relaxes, as we say, to the quantum distribution, that will have taken place eons ago. If you think this through and you think, well, when would this relaxation have taken place? It's not going to have happened yesterday. You know, the electrons that you have in the lab, it didn't happen this morning. It will have happened at the beginning of the universe, if it happened.
So the process starts when the system gets instantiated into existence, and that's why you have to go back to the beginning of the universe.
Well, I mean, I think the real point is that if you look back, you know, if you follow the history back in time, you know, the electrons, for instance, were maybe, before the solar system formed. You had a star that was. You know, you have nuclear reactions in there with the temperature in there already. If in that star you had electrons that had a distribution different from the Born rule, they would very quickly reach the Born rule. Okay, so you know but there's already been a long history before that. I mean, I'm simply making the point that, well, when would this have happened? Well, it would presumably have happened as far back in time as we could possibly go, because, you know, in all of that history, the violence of those conditions will have made this process happen very quickly. So, you know, it doesn't seem plausible that it will have happened now if before there's already a long period of violence. But anyway, So gone on a long ramble here, but the point is, when I started looking at pilot wave theory, I saw that, well, it gives a concrete model of this heat death or quantum death idea that I had. And I should say there's controversy about this. People in the field, there are other people in the field who won't agree with me, but I think they're wrong. And in the book I explain why they're wrong.
So others in the pilot wave.
I should say that most people, the few people who work in this area, mm-hmm. they usually take the Born rule as a postulate.
Right.
So they say there are three postulates in the theory. There's the Schrödinger equation for the quantum wave, which is what you study in the textbooks. There's de Broglie's law of motion that says that the particles move perpendicular to the wave crest with a certain speed. And then there is the Born rule, the assumption that the particles begin distributed according to the height of the square of the height of the wave. They take that as one of the laws of the theory. Mm-hmm. I think that's wrong. It would be a bit like, if we go back to the thermal analogy, let's take it to be a law of physics that all systems have to be at the same temperature. What? No. I mean, you know, there are the laws of thermodynamics, and underneath those, there are the laws of kinetic theory and so on. The state of global thermal equilibrium, or heat death, has this property that all systems are at the same temperature, but that's not a law, that's a contingency, that's an accident of the state. It would be silly to think that that's a law, and yet, unfortunately, this is what has happened. In this theory, most people take the theory to be the theory in which all systems obey the Born rule. So all systems have the same quantum noise, the same uncertainty principle, and you always get an equivalence to quantum mechanics. I think that's wrong. I think this theory is telling you that, look, in this, you know, there's a larger domain of physics. We're stuck in a small region where you have the Born rule, you have quantum probabilities, you have the uncertainty principle, You cannot use entanglement for superluminal signaling, but those are just properties of this special state that we're stuck in. And the reason we're stuck in that state is because if you start out here, what we know about the violence of the history of the early universe, you will have very quickly have reached here. Okay, I mean, under plausible conditions, if the universe began out here in a more general state, it will have quickly evolved to this state. Okay.
And do you need like an aggressive process to do that evolution quickly? Like,
well, surprisingly, all you really need are just a sum of several energy states. I mean, something like with just a single plane wave like this, you won't get relaxation to the Born rule. But if you have particles that are in a superposition, I mean, some simulations have been done where you have a sum of as little as four modes, a particle in a two-dimensional box with just a superposition of the first four energy states. And it's surprising, you get quite efficient relaxation even just then.
So you don't need, kind of extremely powerful processes to create the relaxation. It
It does happen.
Just with, but once you start to make the system complex.
Exactly. But you see, the reason I emphasize the cosmology side is because sometimes people say, well, why don't we go in the lab? Maybe we can see this happening, see things relaxing to equilibrium.
Yeah.
I say, look, but the things that you have in the lab have a history of violence. They will have relaxed to the Born rule billions of years ago. Anyway, but now going back to the puzzle, the initial puzzle, what I call the quantum conspiracy. You have entangled particles that, the usual way of putting it is that it's as if they're communicating. But they're not really. You can't actually use it to send a signal, but they're kind of communicating, and this is all a bit of a puzzle.
Yeah.
According to pilot wave theory, if you think it through, they are communicating. What happens is two particles are guided by a single wave that exists in a higher dimensional space that describes the positions of both particles. So each particle is moving in three-dimensional space. To describe those motions together, you need three numbers for this particle, another three numbers for this particle. That's six numbers. These particles can be represented by a single point in a six-dimensional space. And the pilot wave that guides the particles exists in that higher dimensional space. Now, what happens? If you look at the mathematics of the theory, if you do something to this particle, if you knock it with something or you switch on an electric field, because of the action of the wave in the higher dimensional space, the distant particle responds instantaneously. I mean, this is very clear in the mathematics of the theory, that it's as if the two particles are one object. And what you do here instantaneously affects the other particle. So if I have, say, a particle in a box here and a particle in a box here and they're entangled, if I do something here, I move the walls of the box or switch on an electric field, this particle, the motion of that particle responds instantaneously to what we've just done.
So when you create entanglement, so you let two systems interact and then so that they become entangled and then move them apart, you're kind of, would you describe it as putting them on the same guiding wave? Or?
Yes, there's one pilot wave that is guiding both particles. And because of that, the motion of one particle depends instantaneously on what you do over here. So these things are deeply connected and connected instantaneously. Now, what happens? You can calculate these details for an individual case. I have a particle here at this position, I have a particle here at this position. If I do something to this particle, I can calculate how this one responds. Now, what happens if I repeat this many times? So I have many copies of these entangled particles. And I do something here and I create a response over there. What happens if I make an average over here? An average of the positions of the particles. What you find is, if my particles are distributed according to the Born rule, so I have a sort of, it's like this, except I have two particles. The joint positions of the particle, or the joint distribution of the positions, matches the quantum wave in the higher dimensional space.
So it's kind of uniform in this
or proportional to the square of the height of the wave in that higher dimensional space. And that is the distribution you assume in quantum mechanics. Okay? If you assume the Born rule, then you find that when you average over here, the average is, the result you get is completely independent of what you do here. So you could think of it like this. Imagine that when I perform this action here, this particular particle moves that way. When I perform the same action, this other particle will maybe move the other way. And I perform it, this particle move that way. If you then look at the overall distribution, you find that, well, some particles have moved this way, some have moved that way, and it averages to zero. The actual net effect is zero.
Yeah, so doing something to the particle in the higher dimensional space in one location is instantly doing it to the other location.
Yes.
But all of these different instantaneous effects are averaging out. So
they average out so that there's no net effect. I mean, a simple analogy here is with coins, which actually is a good, because normally when one talks about these things, one has in mind entangled particles and what are called measurements of spin, that you pass the particle through a magnetic field and it either goes up or it goes down. And in fact, this is an easier way to understand what's going on. You imagine that the measurements that you're making, you're seeing, does my particle go up or does it go down? Whether it goes up or down is affected by what I do here. So maybe you had a particle that was going to go up, but because I've turned a dial here, it changes direction and goes down. There are other particles that were going to go down, and because I turn this dial, they now go up. What happens in this state, in the equilibrium state described by the Born rule? What happens, let's say you have particle, this one was going to go down and this one was going to go up. When I turn the dial over here, they just swap over. Ones that were going to go up now go down, and ones that were going down now go up. And what happens,
from this
the net number, let's say for instance it's the case that half of your particles are coming out up and half are coming out down. If I turn the dial, the particles that were going down now go up and the particles that were going up now go down. You've still got half going up and half going down. You don't notice any difference. That's if you have the Born rule. If instead you break the Born rule, let's say all of your particles were going up. They're all going up. I turn the dial, now they're all going down. You would definitely notice, even at a statistical level, you gather statistics over many experiments. You hang on a second. If Valentini over here, he keeps his dial here, all my particles go up. I want to send you a signal. I just turn the dial. Now they're all going down. So I can send you an instantaneous signal if we break the Born rule. If we're outside of that restricted state.
Yeah.
Now, in fact, I've made an argument that, this is true actually not only in pilot wave theory, but in any deterministic hidden variables theory. In other words, a theory in which there are some unknown parameters that determine exactly what happens. If you look at the statistics of what are called spin measurements, we have particles going up and down in magnetic fields. Bell's theorem is telling you that some of the outcomes there must depend on what you do over here. Okay? Otherwise, it will be a local theory. Okay, that Bell's theorem tells you that some of them must be responding instantaneously to what you do. Now, it's the case that if you assume a certain distribution of hidden variables, you get quantum mechanics. And in that state, when I turn the dial here, some flip from down to up, and some flip from up to down. And the number that flip this way is the same as the number that flips that way. There's a balancing act going on, and the net change is zero. But that is true only in that special state. If the distribution of hidden variables is different, then this detailed balancing gets upset. And when I turn the dial here, maybe more will flip from down to up than flip from up to down, and there's a net signal. So the conclusion here, can't send instantaneous signals, is not a law of physics. It's an accident of the special state that we live in which the distributions of particles, or more generally the distributions of hidden variables, take a certain form. And in pilot wave theory, you can understand why they take that form in terms of a complex evolution from the past. So it's a little bit like, going back to the thermal analogy. If I have a box of gas and all the molecules start in one corner of the box, and I let it evolve, well, they bounce around and eventually they spread uniformly over the box, and that's thermal equilibrium. In pilot wave theory, if I have a system with some complexity, and not even very much, if I start out with a distribution that's different from the shape of the quantum wave, it very rapidly reaches it. So, to me, the reason I found this attractive is because it explains the quantum conspiracy. Why is it that we seem to be in a world where it's as if there's something going on behind the scenes that is acting instantaneously, but you can't actually get your hands on it and control it? Why would that be? Here, there's an answer. It's an accident. It's not a conspiracy in the laws of physics. It's just an accident of the state that we happen to be in. In that special state, you can understand why this extraordinary superluminal process is going on behind the scenes, why we can't see it. Now, if you take all this seriously, it of course invites the question, well, all right, there's a certain plausibility to this. You can explain why we see what we see, but how are we ever going to find hard evidence for this? Now, it seems to me that if you take this theory seriously, the theory is telling you, look, the physics that we're seeing is very restricted. It's the physics of this Born rule. There's a more general physics that can exist and that may have existed in the remote past. We need to look for it. So a lot of the work that I've done has been on cosmology, looking for evidence for possible violations of quantum mechanics and violations of the Born rule in the very early universe. The idea is, if we went back to the very beginning, if we're close enough to the beginning, if we did such an experiment, we wouldn't see the usual pattern. Now, you might say, well, how on earth are we going to do that? Well, it so happens, according to inflationary cosmology, there is a way to test the Born rule in the very early universe. And the way it goes is like this. There is a relic radiation left over from the Big Bang. You see it all over the sky. It's called the cosmic microwave background. It's a radiation that has a temperature of about 3 degrees above absolute zero, and it's mainly in the microwave region. The temperature of that radiation is almost but not quite uniform. There are small ripples, about 1 part in 100,000, something like that. There's small non-uniformities of temperature. Now, according to our understanding, the reason that the temperature is not completely uniform is that when that radiation was formed in the early universe, the distribution of matter and also the curvature of space describing gravity was not completely smooth. There were small non-uniformities in the distribution of matter when the radiation. So the radiation it has on what we see in the sky is an imprint of a small inhomogeneity, as cosmologists put it, in the early universe. Now, where did that come from? According to inflationary cosmology, those small inhomogeneities in the density of matter grew from even smaller inhomogeneities that were generated in the very early universe by the Born rule, by quantum fluctuations in a scalar field. There's a simple field called the inflaton field, which it has a certain probability distribution for the field to be stronger or weaker in different places. And using what's called quantum field theory, we can calculate the spectrum of the field fluctuations, and we use the Born rule. If you use the Born rule to calculate those fluctuations are believed to have seeded the small inhomogeneity in the distribution of matter at later times, which then is imprinted on the cosmic microwave background. So what does that mean? According to inflationary cosmology, the statistics of what we see in the sky is ultimately generated by the Born rule. If the Born rule was broken for the inflaton field at very early times, it would have a knock-on effect and you would see anomalies in the cosmic microwave background. I mean, that's clear, assuming inflationary cosmology is correct, which, of course...
So inflationary cosmology implies that there's an inflaton field.
Inflationary cosmology assumes that there's an inflaton field whose energy density drives a very rapid expansion of space at very early times.
And because that is governed by quantum mechanics, you then
because that field is governed by quantum mechanics, it inevitably has some quantum fluctuations. And if you assume the Born rule, you get a certain spectrum. And this was, widely seen as a great success for inflation because the spectrum that you calculate, seems to be more or less what you need to explain what we see. Okay. Now, and it is the leading theory of cosmology today. Some people think that it's maybe we should be thinking about something else. But anyway, if it's true, it provides an opportunity to test the Born rule in the very early universe. So now, some of the work I've done, remember I talked about quantum relaxation for particles in a box, that they start out with a distribution different from the Born rule and they very rapidly evolve to the Born rule. With Samuel Colin, a Belgian physicist, he was a postdoc with me in the US some 10 years ago, we did some computer simulations for a field on expanding space. So we're modeling the very early universe. So we have a scalar field, it could be something like an inflaton field, but space is expanding. So according to our understanding of cosmology and Einstein's theory of gravity, space is not a fixed thing. It can expand and contract. And in fact, our universe, it's still expanding. But in the very early universe, it's expanding very rapidly. And we wanted to study how does this affect the process of relaxation. So we start out with a quantum field whose distribution is different from the Born rule. And we calculate, so it's just like doing the thing for the particles in a box, except it's for fields and it's on expanding space. What you find is very interesting. So the field, you can decompose it into different frequency components, long wavelength, short wavelength, and you can study the evolution for one component at a time. What you find is when the wavelengths are very small, you get the usual relaxation, just like the particles in a box. You get this incredibly rapid approach to the usual statistics described by the Born rule. When the wavelengths are longer, the relaxation is suppressed, it's slowed down, and it doesn't quite reach the quantum distribution. Now you may say, what do you mean by short, what do you mean by long? On an expanding universe, there's a length scale called the Hubble radius, which is it's a typical length scale associated with the expanding space. And today it is huge. This is a cosmological scale.
Mm-hmm.
What you find is that when the wavelengths are shorter than the Hubble radius, they relax very quickly, and you very quickly reach the Born rule. When the wavelengths are longer than the Hubble radius, the relaxation is suppressed. It takes place to some extent. It doesn't completely relax, and this effect is more pronounced at longer wavelengths. So now we have, and of course, as always with these things, you can only do calculations with a simplified model.
Yeah.
Okay, so but within the limits of this model, you have what looks like the following prediction: that if the universe starts out with a distribution different from the Born rule, what do you expect to see today? Today we expect to see the Born rule at short wavelengths, such as what we see here in the lab, anything larger than cosmological scales. But at very large cosmological scales, you would expect to see a deviation from the Born rule. So you would predict that in the cosmic microwave background, assuming inflationary cosmology, that it's essentially mapping the Born rule into the sky, you would expect to see anomalies at very large scales. And the kind of anomalies you would expect to see less noise on large scales. It so happens in 2013 the results from the Planck satellite were announced, and the team announced what they called their most puzzling finding, in quotes, that at very large scales there is what's called a large-scale power deficit, that the statistics of the small non-uniformities in temperature in the microwave sky, if you look at it on large scales, there are less, in a certain sense, less fluctuations than you would expect. Now, I hasten to add, this is it was controversial then, and it's still controversial, because at large scales, the data are sparse and very noisy. And some people think that this anomaly is just a statistical fluke, that there's nothing really there. Other people think there's some new physics there that we need to explain it. In any case, I mean, I could talk also about, with some other colleagues, we did fitting our predictions to data from the cosmic microwave background. Our prediction with a deviation from the Born rule at large scales, it fits the data just as well as quantum mechanics. And you can't really say whether one is preferred or not preferred.
Yeah. So it's not a big enough
It's not a big enough deviation to say anything firm. And in fact, whether these anomalies really exist is still controversial. Hopefully, this will be resolved. There is a Japanese satellite being launched, I think in 2032, the Lightbird satellite, is going to look in particular at the polarization of the cosmic microwave background that will hopefully resolve. I mean, there's a lot more I could talk about, but there are also anomalies with polarization at long distances which don't seem to quite match the anomalies that you get just looking at temperature, which is again something you could expect in pilot wave theory. Anyway, hopefully the controversy will be resolved at some point. But at the moment, what I can say is that the theory predicts the right kinds of anomalies, at least right in the sense that these kinds of anomalies have been reported. But the data are too noisy to really draw any firm conclusions. And as I said, even whether the anomalies exist is still controversial. But you see, this is just stepping back, back to the bigger picture. What drove my curiosity from the beginning? This bizarre situation that we seem to be in a world in which it's as if things are communicating instantaneously, but you can never really use it to send a signal. Thinking about this, it seems to me that at least one rational explanation for it is that look, there is something going on behind the scenes. You can't control it and use it because we're stuck in this special state where everything is imbued with this same quantum noise, or this sort of uncertainty, statistical noise that's associated with the Born rule. And it's because of that special state that when you try to send an instantaneous signal, you get a sort of statistical averaging occurs in which the signal just averages to zero. You know, some of your particles are being knocked upwards, some are being knocked downwards. You don't notice any difference. And this is just an accidental feature of this special state that we're stuck in. And we're in that state because of the history of the universe, that if you begin outside of that state, you naturally end up in that state. But looking at the details, it turns out that at very long wavelengths, you would expect, in a sense, very long wavelengths for fields in the early universe do not end up in here. Short wavelengths do, but the long wavelengths don't. And it so happens that there are long wavelength anomalies in the cosmic microwave background, which may have something to do with this, maybe they don't. So,
so gathering data using telescopes is kind of one avenue towards finding deviations from quantum mechanics. With your theory, are there other possible avenues for seeing deviations?
Well, so ideally what you would want is to have particles here and now that break the Born rule, and that when you fire them at a two-slit experiment they give you something different, and when you entangle them I really can send you a superluminal signal. Here's one way in which that might happen. Going back to the idea that relaxation to the Born rule took place in the very early universe, imagine if you had some particles that stopped interacting with other things at very early times, and with a very simple quantum wave. That's a bit of a, may sound like a very tall order, but bear with me a second. Such particles will not have reached the Born rule. Okay, they will have maybe begun to relax, but then if they stop interacting with other things and they have these very simple wave functions, they could survive just floating around in what is almost the vacuum of space, untouched, and still carry traces of deviations from the Born rule. Now, this may sound like a very tall order, but according to prominent theories of particle physics, we expect particles, for instance, according to supersymmetry and theories of supergravity, there is a sort of what's called a supersymmetric partner of the graviton that describes gravity, called the gravitino, which is expected to have what's called decoupled at very early times. I mean, the very earliest moments of the Big Bang, it will have stopped interacting with other things as the universe cools significantly below the Planck temperature. It will just not be interacting with anything. And many physicists, particle physicists, expect that the universe today is filled with a sea of such particles. If they're not gravitinos, there'll be something else. But it is widely expected that the universe today contains relics from very early times that we can't detect directly. And in fact, the astrophysicists tell us that the universe contains a large quantity of what's called dark matter that we can't see directly but has gravitational effects. And there's a big puzzle as to what this dark matter is. And the leading theories say that dark matter consists of relic particles left over from the early universe. Now, these particles don't interact with anything else except through gravity. How can we see them? Again, according to the theories, it is expected that these particles will eventually decay or annihilate to produce photons. It could be X-rays, gamma rays. And there are experiments, satellites, looking for telltale signs of such radiation. And in fact, from the center of our galaxy, there is what's called the gamma ray excess. There's an excess of gamma rays, which was unexpected. Some people think that it is dark matter that is decaying or annihilating.
Mm-hmm.
Some astrophysicists think maybe it has a more mundane explanation. But in any case, if it's not the galactic excess, maybe tomorrow people will announce evidence for X-rays or gamma rays from dark matter particles that are relics from the early universe and that are now disintegrating. So here's a possibility. If the relic particles, as I said, decoupled or stopped interacting very close to the beginning, it seems possible that they may not have reached the complete Born rule state. They can still have deviations from the Born rule. Now, those particles, when they decay or annihilate and produce photons, you would expect the photons to inherit this deviation from the Born rule. So here's an idea. If it's confirmed that we have, here are X-ray photons coming from dark matter decay from particles that we believed were left over from the very earliest times, I would suggest that we take those X-ray photons and we do something like this experiment.
Mm-hmm.
Let's test the Born rule for those photons. I have these photons that are coming, for example, from the center of the galaxy. They may be from disintegrating dark matter. Do they obey quantum mechanics? Do they obey, in particular, the Born rule? We could test that by, doing simple experiments such as this, or probably more simply testing their polarization probabilities. Is another thing one could do. Now, to do this, you would need a dedicated satellite in space with some sort of onboard interference experiment or something that could test the Born rule, because the X-rays, of course, if they hit the Earth's atmosphere, they'll be degraded, and so
you need to catch them.
And this is why, of course, the X-ray observatories, they are out in space. So the Fermi satellite, for instance, which has reported the gamma ray excess, I hope I'm remembering that rightly, it's some years ago now. It is out in space, so you don't have the obscuring effects of the Earth's atmosphere. What you would need is on board such a satellite, something like this experiment. Now you might think, well, hang on, how are we ever going to do this? It so happens that last summer, June 2025, a German satellite, it's called the Quick 3 satellite, it's a small satellite, was launched with the aim of testing the Born rule in space.
Oh.
It has an onboard interferometer. It's a sort of more complicated version of this that is designed to test the Born rule. But let's not get too excited. It's not going to test the Born rule for photons coming from the center of the galaxy or anything like that. It has an onboard photon source, a source of optical photons, so in other words, visible light. But the idea, it's a sort of proof of concept. Let's test the Born rule in space. And they were supposed to have released preliminary data at the end of last year. They haven't yet, so I don't know if something's gone wrong. Anyway, we're waiting. But of course, no one's expecting to see a deviation from the Born rule. But the point is, once you have something like this up and running, we can do experiments to test the Born rule on a satellite in space. At some point, if there are some photons that are possibly from disintegrating dark matter or from whatever source that you think might be worth testing, some distant astrophysical source, you could then, with such a satellite, you could perform experiments to see if those photons obey the Born rule. And in fact, I won't go into this too much because it will be too much of another long story, but there's another avenue of research I've been exploring more recent years, which is the possibility that gravity can somehow create deviations from the Born rule. So normally, the relaxation process occurs, it's a bit like the coffee cup. The coffee cools to room temperature and that's it stays there. It's not going to heat up again. The relaxation process we've talked about, you have deviations from the Born rule, They relax, you end up in this region where you always have the Born rule. It's conceivable in some exotic circumstances, effects coming from quantum gravity could upset this state of equilibrium and drive you out of it, and you know, almost be as if the coffee that's cooled to room temperature starts to heat up again by some, it seemed like a miracle. But anyway, there are reasons for thinking that, let me be specific. Hawking showed us that back in the 70s, theoretically, that when a black hole forms, it actually has a temperature. And if the black hole is very small, it has quite a high temperature and can radiate what's called Hawking radiation. Now, and the more it radiates, the smaller it gets and the hotter it gets, and you end up with an explosion. Now, there's abundant evidence for black holes in space, including at the center of our galaxy, but they're huge, millions of solar masses. It is believed that the universe, just as we expect the universe to be populated by relic particles from early times that we can't see, we also expect there to be a sea of what are called primordial black holes that will have formed in the very early universe. Remember, in the early universe, it's not completely uniform. In some places a bit more dense, some places a bit less dense. If you look at the statistics, occasionally it will happen that the density is so high that it ends up collapsing to form a microscopic black hole. This was calculated by Hawking, also Bernard Carr did a lot of work on this back in the 70s, 80s. You know, you can calculate this process and show that you would expect there to be a sea of primordial black holes, very small black holes in space. And in fact, some people think that dark matter might be composed of primordial black holes. It's also quite a prominent theory. I think Bernard Carr is still one of the main proponents of that theory. And it's a very plausible theory. Now, the point is the following, that primordial black holes, if they have the right mass, about 10 to the 15 grams, I think, the lifetime matches the age of our universe. Oh. So in other words, they should be exploding around now. Oh. Okay, primordial black holes that formed very near, close to the Big Bang, if the mass is about 10 to the 15 grams, they will be exploding now. And again, people are looking for this. There are satellites in space looking for X-rays and gamma rays that could be telltale signs of exploding primordial black holes. Now, what has this got to do with the quantum and the Born rule? The point is, without going into too much detail, if you're interested, chapter 8 of the book and chapter 9 of the book talks about this, that owing to certain quantum gravitational effects, in the final stage of black hole evaporation, it's possible that the radiation that comes out will deviate from the Born rule. Oh. So that radiation, those photons, if we could, in an ideal circumstance, pass them through a two-slit experiment, we wouldn't see the usual interference pattern. We would see something different. So the suggestion is, if tomorrow the astrophysicists announce that, we've, eureka, we found radiation from exploding primordial black holes, I would say, good. Let's take that satellite with the interferometer, let's get those photons in and see if we can do an experiment to test the Born rule. As you will have noticed, all of the thing that pilot wave theory can allow that other interpretations do not allow is a violations of the Born rule. Okay, in standard, in other interpretations, the Born rule is a law of physics. You're never going to see a deviation from the Born rule. If you fire one particle at a time at a two-slit experiment, you will always see this pattern. And some people may say, explain this with parallel universes. Others will say the particle appears when you look at it, but you always have the Born rule. Pilot wave theory, at least the way I see it, it's telling you that the Born rule is just a special case. there is a whole wider physics out there in which this you would not get that two-slit interference pattern.
And if you imagine that, let's say we were able to get these, gather these X-rays or the radiation from the exploding primordial black holes, can we imagine some kind of technology that you could, some new things that you could do using that capability?
All right, how long have I got to explain it? 1 minute, 2 minutes? It's in chapter 10. I'll give you the short the short version. If you allow deviations from the Born rule, you can break the uncertainty principle. Now, a simple way of thinking about this, think of Heisenberg in 1927 when he was first talking about the uncertainty principle. He imagined a microscope. People often call it Heisenberg's microscope, where you say, imagine I'm trying to watch an electron, and I watch it using light. I shine light on it. Now, light is made of photons, and the photons, when they hit the electron, they knock the electron. And there's this whole discussion of, well, how precisely can I watch the electron using light that's made of photons? Roughly speaking, I mean, it's a bit of a heuristic argument, but roughly speaking, what is happening in the standard discussion is that, well, I can't see what the electron is doing precisely because the photons in the light that I'm using to look at it, what they are doing is already not known precisely. So roughly speaking, I'm trying to overcome some uncertainty in the electron. I want to see it more precisely, but I already have the same level of uncertainty in the photons. And so it's a bit like what I was saying about Maxwell's demon. If the equipment, I'm trying to look at the molecular motions very precisely, but if my equipment is at the same temperature, I've got the same thermal noise here as in the system I'm trying to probe, so I can't really get anywhere. Here, what's happening in the Heisenberg microscope is that the photons that you're using to try to probe the electron have the same quantum noise as in the electron. So there's this limitation of what you can do. Now, in pilot wave theory, it doesn't have to be so. I can imagine photons in which the statistical distribution is much narrower than what you could have in quantum mechanics. So, for example, here, if all the particles begin here or close to this point, instead of having this very broad statistical distribution, I could have a very narrow distribution. And so they all end up over here. I can imagine photons where the usual quantum noise is greatly diminished. It's much smaller than the quantum noise. You can show, and the mathematics quite straightforward to work out, if I let these photons interact, let's say I have an ordinary system that obeys the Born rule, and I want to probe exactly what it's doing. I want to observe the trajectory. For example, let's say I wanted to watch the particle as it went through the two-slit experiment, without disturbing the wave function. Okay, now that's normally not possible. If I try to watch what the particle does, I change the wave because I make the particle interact with something else, and I create a sort of higher dimensional wave, and it separates into branches. There's a long discussion. I change the wave here. Maybe there will just be this wave coming through. For instance, if I try to watch what the particle does. So in standard quantum mechanics, it's not possible to watch what the particle is doing without messing up the wave. Not true in pilot wave theory. If I have some other particles which have a distribution with much less noise than the usual quantum noise, what I can do is I can make these particles interact very weakly with that particle, so weakly that the wave is not disturbed. And normally, if this particle has the usual level of noise, this measurement is not going to tell me anything. It's not going to tell me anything about the particle. But
Yeah.
if this particle has much less noise, I can notice, I can see precisely where this particle is. It's essentially, if you imagine I have a distribution here that's so narrow, even though it's interacted only very weakly with that, it has shifted a tiny bit. And because it's so narrow, I notice the shift. So I call this a subquantum measurement. Pilot wave theory, if you allow violations of the Born rule, and if you allow distributions that are much narrower than the usual quantum distribution, you can perform measurements that are not possible in quantum mechanics. I could track the motions of particles without affecting the wave function. No.
So normally when I imagine the mechanism of what's happening during a measurement is that, so say in the double slit experiment, I'd say, okay, if I try and measure where the particle's going, then I become entangled with it, and
No, that is right.
we become correlated, and that's why I only see,
Yes.
I see this distribution, this interference pattern
Will be washed
change.
away. It will be washed away, yes. And your equipment becomes entangled with it and strongly and affects the wave function and changes the whole thing.
Yeah.
If the interaction is extremely weak, the wave function is hardly disturbed. And normally in quantum mechanics, a single weak measurement doesn't tell you anything. Whereas here, if the actual if the pointer, let's say I've got a piece of equipment with a pointer, if I have the quantum wave for the pointer that's like this, but the actual pointer is known to have a position highly localized within that wave, then even though you couple it very weakly to the particle, the pointer moves slightly.
Yeah.
And because you knew exactly where it was, you notice.
Yeah.
You see?
Yeah. So it's like you get very weakly entangled, like you would do if you do a weak measurement.
Yes,
in
but
normal
instead of
quantum
having
theory.
to perform many measurements and then averaging, which is what you do in a weak measurement, you have to do it many times in order to get anything. Just one measurement doesn't tell you anything. Here, one measurement does tell you something.
Right. Yeah.
So I see I'm convincing you. Good. So anyway, but what I wanted to say, you asked about quantum technology. So clearly, if I can do these kinds of things, then it opens up all kinds of new possibilities that are not possible in quantum mechanics. One, of course, is that, well, now you can, with entangled particles, you can send superluminal signals. So, I could have, if we have entangled particles that are shared, say, between Earth and Mars, and normally between Earth and Mars, a radio signal takes up to about 20 minutes to travel each way. So I want to control my robotic lander on Mars in real time. We can't do that now. It takes 20 minutes for a command to reach the lander. In principle, the kind of instantaneous communication would be possible. Which means, of course, you have to revise relativity theory. In a nutshell, instead of synchronizing clocks with light signals the way Einstein did, you would use these instantaneous signals to synchronize your clocks. And there would be a preferred time across the universe. But this is another long story. But other implications for quantum technology. So a big thing now is the developing quantum internet, where there is a technique. People want to be able to send messages to each other in secret in a way that is unhackable. The problem of cryptography. And there's something called quantum cryptography, which is supposed to allow people to essentially share a secret code that they can then use to encrypt messages. But when they share this secret code, it's supposed to be impossible for an eavesdropper to know what the code is. And the kind of way in which this is done, and of course the punchline is going to be that if you can violate the Born rule, you can eavesdrop. on this process, and the security of the quantum internet will be compromised if we can violate the Born rule. But to give an example, so there is a technique, what's called quantum key distribution, developed by Arthur Eckert here in Oxford, 1991. So I have entangled particles, and they fly apart, and they're entangled, and they're in a special state where if you measure the spin up or down over there, and I measure the spin up or down over here along the same axis, we always get opposite results. If you find a particle moves up through the magnetic field, mine will move down. If your particle moves down, mine will move up. They always give opposite results. And in Eckert's scheme, you can use this to create a key that we share. So we repeat this experiment many times. You know, we share these entangled particles, they fly apart. You measure the spin, I measure the spin. When you get up, I get down. When I get up, you get down. If we repeat this many times, you will get a string of numbers, up, up, down, down, up, down, that which you can call 0, 1, 1, 0, 0. I will get the opposite. Okay, whenever you get up, I get down, so we now have you have a secret key, a secret string of numbers. I have the same string of numbers, and we can now use this to encrypt messages and so on. Now, according to Eckert's analysis, it's not possible for an eavesdropper to know what this secret key is going to be, because there is nothing in quantum mechanics that determines what the outcomes are going to be. When we perform those measurements, the up or down result that you get and the up or down result that I get, they're supposed to be completely random processes. They're not caused by anything. Now, according to pilot wave theory, actually, back at the source, when this pair of particles was entangled and start moving apart, there are some hidden particle positions, just like here. There is a definite, the particle starts somewhere within the wave. There's not just the wave. There are hidden particle positions, and if an eavesdropper, Eve, let's call her Eve, they usually call the eavesdropper Eve for whatever reason, if she is able to perform a subquantum measurement, in other words, if she has a store of this sort of non-quantum matter that violates the Born rule, she will be able to weakly couple to those entangled particles and observe the precise location and trajectory. And because she knows where the particles have started, as they fly apart and you perform your measurement and I perform my measurement, she can predict whether you're going to find up or down. And she can predict whether I'll get up or down. Okay? So what I'm saying is Eve, by performing a subquantum measurement at the source, she can predict in advance what this supposedly secret code is going to be. And so it is hackable. What is not, I mean, the usual conclusion is that to hack into quantum cryptography or the quantum internet, you would need to break the laws of quantum mechanics, and seeing as that's never going to be possible, this is always going to be secure. Here, you are violating the laws of quantum mechanics, in particular the Born rule, and you would be able to hack into the system. So the quantum internet would become hackable. And finally, one thing, and I'll just be very brief here, you might ask about quantum computing. Quantum computing, so computers based on quantum mechanics appear to be more powerful than ordinary computers, at least for certain tasks. If I was able to perform subquantum measurements, I would be able to design new kinds of computers that are not possible in quantum mechanics. So specifically, there's something in quantum mechanics that says if I represent quantum states by rays or vectors in a certain space, if the vectors are not perpendicular, okay, if they're like this, it's not possible to distinguish them with a single measurement. In fact, a simple example, I don't need to be abstract geometrical like that. I can imagine I have a quantum wave that is for a cat. And the quantum wave says the cat is dead. Now I have another quantum wave that says the cat is in a superposition of dead and alive. And now I give you this puzzle. I say, here are two quantum waves. Can you distinguish them with one measurement? Well, this wave says the cat is dead. This wave says the cat is dead plus alive. If we look at the cat and we find it's dead, well, it could have been either wave. This wave said it was dead. This wave said, well, it could be dead, it could be alive. So if I measure and find it's dead, well, I don't know which wave it was. If instead I measure and I find it's alive, well, then it must have been this wave. But the point is, if I have quantum states which have a component in common, okay, so here's dead and dead plus alive, so they both contain dead. If I perform a measurement on just one copy of the wave, I can't tell which wave it is, and this is called the problem of distinguishing non-orthogonal states. It's a theorem of quantum mechanics that it can't be done in a single measurement. It can't be done reliably with a single measurement. That breaks down in pilot wave theory. If I have non-equilibrium violations of the Born rule and I can perform subquantum measurements, essentially I can have two different waves that are what's called non-orthogonal, so they're different but they have an overlap, they have a component in common. If you look at the actual trajectories or the motions of the particles associated with these waves, in general the motions are different. So if I can track the trajectories inside the waves, I can distinguish the waves. So what can happen is I could have a new component of a computer, if you like, that sends in a quantum state, and I want to know which of two states it is, but the two states are not orthogonal. They're not normally distinguishable. You could have what you might call a subquantum gate that can distinguish the two states. So what you can do is you can consider new kinds of computers that can do things that are not possible even in quantum mechanics. And it's probably the case that such computers will be more powerful. But this has not been studied properly yet. A comparable study was done in the 90s. Abrams and Lloyd considered something what's called nonlinear quantum mechanics, where it's a form of quantum mechanics where the way the wave evolves has is non-linear, which means that I can't just add solutions to create new solutions. You know what I mean, because you're a physicist. But anyway, it's a bit of a technical thing. But some people have considered the idea that the Schrödinger equation, from which you calculate the time evolution of the wave, would contain these small nonlinear terms. And if such terms exist, then states that are initially not perpendicular can become perpendicular, which is not possible in quantum mechanics. And so you can distinguish non-orthogonal states. And they showed how, they argued that this would enable forms of computation that are more powerful than quantum mechanics. Something similar could be done in non-equilibrium pilot wave theory. You can distinguish non-orthogonal states. However, if you want to know exactly how powerful this is, you really need to discuss. I mean, there's a technicality here that hasn't been studied, which is a proper definition of how powerful a computer is requires that you know how do the resources that you need scale with the size of the task.
Yeah.
If the resources scale exponentially, then it is generally considered to just be not a good thing and not useful.
Yeah.
So here, what is definitely the case is that if I have a resource of subquantum matter in a state where the Born rule is violated, I can use that resource to do new kinds of computations that are impossible in quantum mechanics. However, as the computational task that I'm looking at gets bigger, how do the resources they need, how do they grow?
Yeah.
Do they grow exponentially, in which case it's considered not useful?
Yeah.
It hasn't been studied. So
Yeah.
formally speaking, the power of these new kinds of computers has not been established yet.
So it's a bit like if you're comparing quantum computers and classical computers, you could say quantum mechanics enables a new kind of computation, which you can do with quantum computers, but that doesn't imply that you can solve problems faster.
Not on
And
its
then
own. You
need to
also
analyse
need to study how the
algorithms
resources
and-
grow
yeah.
with the size of the task. And of course, such studies have been done, and it is concluded that there are quantum computers that are usefully more powerful than classical, at least for certain tasks.
Yeah, but you need to do that step.
That
to
kind of step
analyse.
hasn't been done
Yeah.
yet. So
Cool. And something that you've mentioned is that, I guess in contrast to other interpretations of quantum theory, they usually try and keep the principle of locality as kind of something they want to keep. And in pilot wave theory, you have this action at a distance is kind of accepted as part of it, and that makes it deviate from relativity.
yes, yes.
Is there a path towards kind of can you make pilot wave theory relativistic, or is there an avenue towards doing that?
All right. So, my question would be, well, why do you want it to be relativistic? This is another point of contention. I think many physicists look at pilot wave theory. Probably the most commonly cited reason for why they don't like it is because at a fundamental level it violates relativity. Within the field of pilot wave theory, there are a number of people who have tried over many years to try to make the theory consistent with relativity, even at the basic level of the trajectories, and they haven't really managed to do that. Now, I mean, my take on this has always been a bit different. I mean, I would say the following. First of all, let's look at the argument that, and it's a common argument, you still hear a lot of physicists say this, there's something wrong with pilot wave theory because it violates relativity at the fundamental level. Hang on a second. The fundamental level of pilot wave theory, these trajectories, we're talking about a level of physics that we haven't seen yet precisely, we're unable to control. At the moment, no one is able to observe that trajectory without disturbing the wave function. It's not possible to perform a subquantum measurement because all the equipment we have has the usual quantum noise and so on. So, if this level of physics really exists, it's at a deeper level than we're able to experiment with. All right? Now, relativity was formulated in 1905 in response to the experiments of the time. It's consistent with the experiments that have been performed so far. None of those experiments probe this deeper level. They're essentially averaging over the Born rule. That's what they see. And what they see is consistent with relativity. So now, I will put it to you. There is abundant experimental evidence for relativity at this level of physics. If we're now talking about a deeper level of physics that experiments have not probed yet, is it rational to say that that deeper level must obey relativity? It doesn't seem to me to be a scientific argument. We don't have any experimental data for this level yet. It's a hypothetical level.
Yeah, I suppose the argument is saying that there's a principle at the relativity obeys, and saying that kind of expecting that principle to still apply at that deeper level, but it hasn't been investigated.
But why would you expect it to apply at a deeper level? I mean, the history of physics is full of situations where you've got, Newton's laws apply at the level of this room, they don't apply at the level of atoms. And one can multiply many examples.
Yeah.
It's not to say that it couldn't happen. It might happen that, we probe a deeper level of physics, and relativity is still true. Okay, fine, that could happen, but it might also not happen. What I object to is I was going to say argument. To my mind, it's not an argument, but it's presented as an argument that somehow there's abundant evidence for relativity. It's passed every test. It's a fantastic theory, the precision, and so on and so on. And so, at this deeper level that nobody has really been able to experiment with yet, it must also apply. That just doesn't make any sense. That is not I'm sorry if I sound a bit harsh, but I think that is actually scientifically illogical. It will be fair enough to say there might be a way to keep relativity at this deeper level. Mm-hmm. Let's try and find it. Fair enough, and good luck if you manage. But it might not be. And I would say that actually the arguments are very strong to expect the opposite. If this deeper level exists, it is telling you, at least in the way I understand it, that it is possible to send signals instantaneously, faster than light. The only reason we can't is because we're stuck in this special state. There's mm-hmm. nothing in the laws of physics that says you can't signal superluminally. According to this theory, if we find matter that deviates from the Born rule, we will be able to signal instantaneously. And so, that if you assume that relativity is still true, according to the equations of relativity that tell you how measurements of time and position change from one observer to another, according to those equations, if I send a signal to you instantaneously, mm-hmm. a moving observer could see that signal going back in time. And most physicists regard that as paradoxical. You shouldn't be able to signal into the past. Mm. Okay? So most physicists conclude superluminal signaling must be impossible because using the equations of relativity theory, you would then get these paradoxes, signals going back in time. However, one can just as well say, well, maybe there's nothing wrong with superluminal signaling. It's just that the equations of relativity are wrong. Mm-hmm. In fact, if you look at the equations of relativity, the way they're set up is there is the issue of how do you synchronize clocks when they're far away. And the way we're usually taught to do it, following Einstein in 1905, is that you should use light signals to synchronize clocks, even when they're moving. Mm-hmm. Now, if you look at this from the point of view of a theory in which there is a preferred state of rest with instantaneous signaling that you would use to synchronize clocks, if you then think, well, what is happening in relativity when people synchronize clocks with light signals? The answer is the moving observer has synchronized their clocks incorrectly. They're using light signals to synchronize clocks. Mm-hmm. They're not correctly synchronized. So now what happens? Because it can seem like such a catastrophe to say, a signal appears to move backwards in time. Mm-hmm. You think, well, this is how we're ever gonna swallow this. It's actually quite straightforward. Nothing is going back in time. All that has happened is that the clocks were not synchronized properly. This clock is set behind this clock. So if a signal travels instantaneously, mm-hmm. it seems to arrive before it left. Now, if that sounds crazy, we have the same thing going on the Earth's surface. If I get on a plane in Paris and I fly to London in half an hour, the clocks in London are set 1 hour behind the clocks in Paris. All right? So I can set off at 2 o'clock Paris time, and if my flight takes half an hour, I can arrive in London at 1:30 London time. I've gone backwards in time, holy smokes. No big mystery, it's just the clocks in London were set an hour behind. Mm-hmm. And according to, if you think this through, pilot wave theory requires that there is a preferred state of rest and that the instantaneous signals, they take place you would use the signals themselves to synchronize clocks. Now, when the moving observer who has done the usual synchronization and he's in a panic because he's seeing your signal going back in time, there's nothing paradoxical or really problematic. It's simply that the clocks were incorrectly synchronized. Now, I mean, if I can maybe just add one other thing on this, because people often get very nervous about the idea of giving up relativity. You know, as students, you have to get your head around relativity early in your undergraduate career, and at the beginning it's difficult, and eventually you get used to it. To somehow have to sort of unlearn some of that can seem like a nightmare. It's actually quite straightforward, because if you look at the history of it, so that transformation, the way you relate positions and times for differently moving observers, as you know, it's called the Lorentz transformation, named after a Dutch physicist called Lorentz. Why is it named after him? Why is it not named after Einstein? You would have thought, why is it not called the Einstein transformation? The answer is, if you look at the history, is because Lorentz worked it out before Einstein did, with some help from Poincaré. Now, but Lorentz's interpretation was different. The way Lorentz looked at it, Lorentz thought that there is a preferred state of rest that is associated with the electromagnetic field, or the ether, as they called it at that time. And Lorentz showed, and the mathematics is exactly the same as in standard relativity, it's just the interpretation is a bit different. Lorentz showed that if a moving observer resets their clocks and redefines the lengths of their measuring rods in a certain way, they will not notice that they're moving. So there was this peculiar thing, or, you know, I'm talking about around 1900, there was this puzzle that the understanding was that there's an ether, there's an electromagnetic field, and you might expect that if we were moving through the ether, we would somehow notice. And people did experiments, the Michelson-Morley experiment in the 19th century, trying to detect the motion of the Earth through the ether, and it gave a null result. People were puzzled. Eventually, people realized, what Lorentz and Poincaré essentially realized, that if you look at the equations for the electromagnetic field, Maxwell's equations, they contain a mathematical symmetry whereby a moving observer can redefine positions and times in such a way that you appear to see the same laws of physics and you don't notice that you're moving. Now, for Lorentz thought there was a true rest frame, and this symmetry was a sort of peculiarity of the laws of physics, where, you know, if you define things in a certain way, you can't notice that you're moving uniformly. Einstein's real innovation in 1905 was to reinterpret this and to say there is no true state of rest. All of these differently moving observers, they see the same laws of physics. They're all equivalent. There is no preferred observer. And that was arguably a good move at the time. You know, so, and again, but what I wanted to say is that the mathematics of the Lorentz view is exactly the same as the mathematics of the Einstein view. The formulas are all the same. It's just, so it's not, so what I want to say, it's actually, once you get used to the idea, it's quite trivial to look at things from the Lorentz point of view. It's just a shift of perspective. The mathematics is all just the same. But the philosophy is different. Now, what I'm saying is that, seeing as now, given the evidence that we have for non-locality, and given the suggestion that, well, if there is a deeper hidden variable level, or something like in pilot wave theory, where there would be instantaneous signaling, then the Lorentz view makes more sense. You know, one simply has to go back and say, well, actually, in a sense, Lorentz was right after all. There is a preferred frame, which, at the level of physics that we've probed in the 20th and early 21st century, we can't detect that frame because we can't see these superluminal processes. So, with all that roundabout discussion, what the point I'm really trying to get across is that to, in a sense, reverse relativity and go back to this Lorentzian sort of point of view is nowhere near as hard as you might think. It just requires a shift of perspective, and I think from pilot wave theory perspective, that's the natural view to take. So what I would say, you asked, is it possible to make the theory agree with relativity? Well, first of all, I would say, well, what's the motivation? There's no evidence that relativity must be true at a deeper level for which there's yet no experimental evidence, obviously. And seeing as at this deeper level there is instantaneous signaling, well, it would seem odd to require relativity because you're going to create these problems.
And if this theory is turns out to be the right theory for beyond the quantum,
yes.
What would the implications be for, say, quantum gravity, or kind of the understanding that?
So, I mean, quantum gravity is interesting because there's a long history. I mean, I'll try not to go off on too many details, but quantum gravity there's a peculiarity of the theory from the very beginning, when it was formulated really essentially in the 1960s by Wheeler and DeWitt. They found so in quantum gravity, what you're trying to formulate is a quantum theory of the curvature of space. So according to Einstein's understanding of gravity, gravity is a manifestation of the curvature of space. Now, you want a quantum theory of the curvature of space. Now, if you apply the usual rules of quantum mechanics to Einstein's theory of gravity, you get something that's a bit like the Schrödinger equation for a quantum wave, but there's no time involved. So the usual quantum wave, it evolves in time. You see, it starts out as a plane wave, it hits a screen, it evolves, it sloshes around. According to canonical quantum gravity, the quantum wave is just static. There's no time dependence. And there's been a long history since the 60s of trying to make sense of this. People argue, in fact, DeWitt argued that there isn't really any such thing as time. That it's only when you make the gravitational field interact with certain material systems that we call clocks that you get certain kinds of correlations that give an appearance of time. And if that sounds obscure, I think it is obscure. It is obscure. And people have been trying to make sense of this for decades. And I should say that there are some prominent people who think that is the way to go. Carlo Rovelli, who kindly wrote a very nice comment about my book. He's a very open-minded sort of person, but you know, Carlo is one of the main proponents of the idea. Well, actually, even though I think his view has perhaps shifted a bit, or at least become more nuanced in more recent years, but he's often associated with the idea that fundamentally there's no such thing as time, and that time is somehow emergent. I think maybe Carlo nowadays would say that time is really more subtle than we think it is. But in any case, there's a long story there, but the short version is that in quantum gravity, there's just, like in quantum mechanics, there's just the wave, which is problematic enough because I have just the wave. How do I account for the fact that when I observe the particle, I see it here and not there? If there's just the wave, how do you explain that? So there's a problem. In quantum gravity, it's even worse. So you have just the wave and it's static. It's not changing. Now, pilot wave theory says, no, there isn't just the wave. There is also, in the case of particles, there is also a particle moving. In the case of quantum gravity, pilot wave theory says there is the quantum wave that is static, but there is also a curved space that is evolving. So the curvature is changing with time. In other words, instead of having a position of a particle that's evolving in time, I have a curved space that's evolving in time. There is a trajectory, if you like, for the curvature of space. And this theory, so it's the pilot wave theory of quantum gravity, was written down some decades ago, and it has been developed. There's a particular school in Brazil, so Nelson Pinto Neto in Brazil has used pilot wave quantum gravity to discuss what's called quantum cosmology. So the theory of the early universe using quantum gravity. Mm-hmm. And his particular interest is in models of cosmology with a bounce, where before the Big Bang there was a contracting phase of the universe that then reached a certain minimum, there was a bounce, and then it expands, and what we see is the expanding Big Bang. But anyway, he's used pilot wave theory to calculate what happens through the bounce. Remember, standard textbook quantum mechanics doesn't talk about anything definite apart from what observers see and measure. So for instance, quantum mechanics won't talk about this particle moving. It will just talk about what you see at the backstop, a blip.
Yeah.
How can I apply quantum mechanics to the early universe when there are no observers making measurements? You imagine if I have a previous epoch of the universe before the Big Bang that's contracting, bouncing and then expanding. How could I even begin to talk about this in quantum mechanics? You can do it in pilot wave theory, and you know, studies have been done. We can calculate the trajectory, how space contracts and bounces and expands again. So there's been it is useful as well. At least it provides you with a much clearer way to discuss quantum cosmology and quantum gravity if you assume that there is actually a trajectory for the curvature of space and not just the static wave.
Cool. And maybe just as a kind of final question, what do you think are the kind of interesting open problems to be developed with developing the theory further?
Well, look, you know, to my mind, the big issue is to find a violation of the Born rule somewhere.
So it's the experimental implication.
To my mind, look, if you're going to make a theoretical proposal like this that is, you know, so far-reaching, you know, I think it really is incumbent upon you to put in a lot of effort into actually finding experimental evidence for it.
Yeah.
You know, I mean, I could, for instance, go away and work out all the details to figure out, well, how powerful these new kinds of computers are really going to be. But at the end of the day, well, what's the point if maybe it turns out there's nothing in this theory anyway?
Yeah.
So
that's the kind of most pressing.
For me, the most pressing thing is we really need to find a way out of this state that we're stuck in. And you know, the early universe is still a possibility. I mean, there is going to be new data from future satellites that may settle the questions about these anomalies. There is also more detailed calculation. I mentioned at the beginning the calculations that we've done, certain simplified models. There's a lot more work to be done there to refine the predictions for what we would see in the cosmic microwave background. That's one avenue. Another is refining these ideas about how, you know, how I mentioned that there are some effects coming from quantum gravity. I mean, I talked about how in quantum gravity there is a static wave. There has to be a certain approximation from quantum gravity where you can recover the usual sort of time evolving waves that we see in the lab. And there is a way to do that, but if you do that, you find that there are small correction terms that change the Schrödinger equation for the wave, which people have calculated back in 1991, Kiefer and Singh, calculated in effect small corrections coming from quantum gravity to the evolution of the usual waves you'd see in the lab. It goes without saying the corrections are so tiny, there's no hope of measuring them now. But some of those terms are, to use the technical term, non-Hermitian, which you will know that means they're not allowed in quantum mechanics. A non-Hermitian correction in the Schrödinger equation means that probabilities will not remain conserved. So if I have, coins that are 50% heads and 50% tails, and maybe they become biased and now they're 40% heads and 60% tails, fine, it has to add up to 100%. If I told you I had a whole lot of coins, 30% show heads and 50% show tails, we're going to say, well, what about the other 20%? I mean, you can, what happens, some of these terms that come from quantum gravity break the conservation of probability, and people have tended to ignore them because they don't know what to do with them. In fact, I had a discussion with Carlo last year about these. I mean, the terms are predicted to be there. If you take quantum gravity and you try and break it down to an approximation, where you describe the waves that you see in the lab, there should be tiny terms that break the conservation of probability. Now, those terms in pilot wave theory make perfect sense. If you think through the implication of those terms, what happens is if I begin with a state in which I do have the Born rule, as it evolves, you will evolve away from the Born rule. You will create corrections to the Born rule. And this is what I talked about what I had in mind when I was talking about there's some exotic effects that suggest that when a primordial black hole explodes, that in the final stage of evaporation, the Hawking radiation that is created will break the Born rule. It's because of those terms, those non-emission terms that are not allowed in quantum mechanics that come from quantum gravity. Most quantum gravity theorists, they don't know what to do with these terms. They think, well, maybe they're just some sort of artifact, or they try. In any case, most people don't try to do calculations with them because you can't in quantum mechanics. Pilot wave theory, what I wanted to say, you asked what is there left to do. There's a lot more still to understand about these effects. Precisely how will it affect the spectrum how will it affect the Hawking radiation coming out of a black hole? To what extent will this radiation break the Born rule? Another thing, I mentioned Nelson Pinto Neto in Brazil. He's a good friend, colleague of mine. He won't mind me mentioning. We're actually working on a project in one of his bouncing models of cosmology. As you have a universe that contracts and it bounces and expands again. During the bounce, the quantum gravitational effects will be significant, and these terms will be there. And we're trying to calculate what happens. What we expect to happen is that if I start out with a universe that obeys the Born rule and quantum mechanics, during the bounce, a violation of the Born rule will be created. So as the universe expands, what comes out, at least at the beginning, will break the Born rule. And we're trying to calculate exactly how this happens. So there's a lot more to be understood there. And of course that whole scenario about the possibility of relic particles from the very early universe. I worked on some of those ideas with Nick Underwood, who's a PhD student who worked with me in the US. But there's still so much more to be done. I mean, we showed how relic particles, relic dark matter particles, if they were decaying, that the spectral lines you would see would be anomalous, because you're breaking the Born rule. But again, there's still so much more to be understood. But at the end of the day, my feeling is that the direction, or at least the direction of research that I'm taking, always has in mind the aim of finding an actual breakdown of quantum mechanics. Because as you've had so many people on this YouTube channel with their different ideas about quantum mechanics. And I'm sure it's occurred to you the question, well, how long is this going to go on for? In another 50 or 100 years, are we still going to be? There's still going to be the many worlds people, the collapse people, the pilot wave people, the people who think that it's all just in your consciousness. Are we still going? It seems to me that things will only shift dramatically if we have an experimental breakthrough. some in which, you know, quantum mechanics is shown to actually fail at some point, and there will be the clue as to what the correct viewpoint or interpretation is, hopefully.
Yeah, great. So I think that's a good point to kind of wrap up the podcast. Was there, anything else you'd want to mention, either that we haven't covered or just final word for the audience?
Well, look, I mean, if I was asked what would I want people to really take away from this book, leaving aside all the details, I think that the key point for me is that physicists and students over decades have been told that quantum mechanics is somehow some sort of ultimate theory that you mustn't question, that it doesn't make sense to question it, that you know, and in fact Bohr and Heisenberg argued in the 1920s that in quantum mechanics we'd in some sense reached the limits of what the human mind is able to understand. And in this they were influenced by the philosophy of Immanuel Kant, who in the 18th century argued that there are certain fundamental limits to what the human mind can understand, and that in fact Kant believed that the only physics the human mind can really understand is the physics of Newton. And since the physics of Newton fails at the atomic level, according to Bohr and Heisenberg, the human mind simply cannot comprehend the atomic level. So we've reached the ultimate limits of human knowledge in some way. And in fact, Heisenberg referred to quantum mechanics as the finally valid physics. Popper discusses this in an interesting way in his book, Quantum Theory and the Schism in Physics. He's very critical of Heisenberg for this, saying, you know, you're claiming that we've, in a sense, reached what Popper called it the end of the road thesis. The main thesis of my book, and in fact, the title, Beyond the Quantum, is that we're not at the end of the road. There is something beyond quantum mechanics. It might be something like this. It might be something else. Obviously, if I knew this was true, it wouldn't be research. But I am convinced that there is something deeper beyond quantum mechanics, and that we can find it. And of course, to have a hope of doing that, we really need more people working on it. We can't just have the odd person on their own with one or two students. We need more people looking at this. So I hope it encourages people to be a bit more open about this possibility. Yeah,
well, maybe we'll have inspired some listeners or viewers of the podcast, or future readers of the book to take a look at these ideas themselves. Great. So that was a really interesting discussion, and I liked that it kind of came from kind of understanding non-locality as like the initial point, because usually we start with the measurement problem, which is kind of a different direction. But
that was not really my motivation.
Narrative,
and in fact, if you had asked me about the measurement problem, you know, people often say, you know, that this kind of theory is being introduced to solve the measurement problem. You're introducing these trajectories to solve the measurement problem. That is a travesty of history. The trajectories were there in 1923. De Broglie had a simple pilot wave theory in 1923. What happened is, he had the trajectories and the wave. What happened in 1926, when Schrödinger got interested in de Broglie's work, is he developed the correct equation for the waves, and he discarded the trajectories. What actually happened historically is that the measurement problem was created by Schrödinger when he dropped the trajectories, because if you remove the trajectories and you just have the wave, I fire a particle in and then I find a blip here. How do you explain the blip? Why did it land there and not here? Or why was it not spread out everywhere? Where did that blip come from if there's just a wave? It's an obvious objection. In fact, there's a letter from Pauli to Bohr that I quote in the book, where Pauli was known for being quite blunt in his, but very acute. he was scathing about Schrödinger. In fact, he was very complimentary to a paper of de Broglie's that had appeared. This is 1927. And he says, you know, de Broglie's paper is on a much higher level than what he called, quotes, the childish papers by Schrödinger, who still believes he can make do with just the wave, without material points. I mean, it was an obvious objection. If you have a theory like this, well, there is no measurement problem. The measurement problem, it's not that you solve the measurement problem. There never was a measurement problem. You know, the particle comes in, you get a definite outcome because of where the particle started. What happens if you say, oh, let's forget about the trajectories and just have the wave? Then you've got a measurement problem. And then when Bohm came along 25 years later and revived de Broglie's theory, he gets accused of adding extraneous structure in order to solve this measurement problem. This is a historical nonsense. Bohm was just restoring what Schrödinger had removed. He was just putting back what de Broglie already had in 1923. So, you know, I would have said, because people tend to say that, well, you know, you're adding this extra structure to quantum mechanics to solve a particular problem, and that's unlikely to be a good way of doing science. I mean, it's historically just wrong. You know, the pilot wave theory was there before quantum mechanics and before the measurement problem. So, you know, if you had asked me about that, I would have said, you know, it's not being introduced to solve the measurement problem. It's all the other way around. The measurement problem was created by Schrödinger, who removed the trajectories from de Broglie's theory. But anyway.
Well, it was going to be my question near the beginning, but we've ended up answering it at the end.
Yes.
So great, and thanks for doing the podcast.
My pleasure.
And,
my pleasure.
Thanks to our audience for joining, and we'll see you next time for more episodes of the Quantum Foundations podcast. Bye.
Thank you.